right, let's get going. Welcome to another edition of the FEM at LLNL seminar series. It is our honor and privilege today to have Professor Paul Fischer here. Paul really needs no introduction. He's one of the gurus, I would say, big names in high-performance computing and high-order methods. Written the book on some of these topics, and it's really a great person to collaborate with. I've had the pleasure to work with him on the CEED project. He spent a lot of time at Argonne, and now is a professor at University of Illinois at Urbana-Champaign. And as always, he's on the cutting edge. He's going to tell us about his perspective to exascale. Really looking forward to it, Paul.
Okay, thank you. All right. Well, I had some grand designs when I wrote this title and abstract, and we'll see if I think we will accomplish some of that. Let's see. It is great to be here. I think this is the first live presentation, well, aside from lectures, the first seminar I've given live in 2.5 years, and it's the first time I've seen Zanio in person for 2.5 years. So very, very nice to be back here. So I'm going to talk, so the title is Exascale User's Perspective. And my very last couple of slides really kind of will cement that idea, I think. But I'll kind of talk about that throughout. And as I mentioned in the abstract, this is seen through the context of NEC 5000, NekRS. And NekRS and our whole exascale effort, I would argue, I mean, we might have done it anyway, but it's really been enabled by CEED and by the team that, that has come together for CEED. I think it's not only as a project, it's been very successful. From my own selfish standpoint, it's been incredibly successful. I mean, I've just been really lucky that we have everybody that we do on the project, and that we're all pushing each other forward, and we kind of know where we are. We're self-gauging, so we know that we're doing a good job. Otherwise, how would you know, right? If you're just working in your office, you're like, oh, I don't know. So this, the development effort here, so a list of developers not in any real particular order. Stefan Kirkmeyer has certainly written the most lines of code for NekRS, and probably Tim Warburton next, although the whole ACA team and the libparallel team has contributed to that. So libparallel was the genesis of NekRS, along with NEC 5000. Obviously, you'll see that we understood how to scale NEC 5000. And so then several developers also here. Ananias Tombolidis has been responsible for a lot of the physics, and Misun Min has done a lot of the work in scaling. Eli Marzari driving our applications. Graduate students Malachi Phillips, Thelina Rathnayaka, Yushan Wang, big contributors. James Lattis, a huge contributor to NekRS, and his code is still central to everything we do. And Alex Obapko also is a major, in some sense, user/developer. So, for example, this simulation is one done by Alex, and it's one of my favorites. First of all, the movie goes on and on and on. There's a lot of flow going on here. There are 3 passageways. There's this main vessel. It's a vein, and then there's a port here that has flow going in the main, the center part, and then there's an annular region where flow is going out, and the annular region is fed by a hole in the sidewall. And the idea is that the incoming blood is coming from a dialysis machine, and it's been clean, and you want to be sucking out the blood that needs to be clean, and you don't want those to mix. And so the question is, how would you design it so that they don't mix? And at certain junctures in this movie, you can see that the flow gets sucked in and then sent up the annular region, and it goes very fast. So this problem has a ton of timescales. It's got very fast flow in the annular region, obviously not so fast flow here where it's turbulent. You'd think, oh, all the action's here, but in fact, probably the rate limiting step, the CFL constraint, is here in this granular region. So these are the kinds of things we want to be able to do. This one was actually done with NEC 5000. I'll go on to the next example if my advance is working. Hang on a second. For some reason, I can see. Okay, it did work. All right. So here's another one. This problem actually fascinated me for many, many years. When I was at Stanford, they had built a transparent cylinder, a sapphire cylinder, and they were so excited because they were going to be able to see what compressed turbulence looks like. And my advisor said, "We don't even know what compressed turbulence looks like," and that was always in the back of my mind. Can I see what compressed turbulence looks like? And with Ananias's help, this involved, he had developed the low Mach formulation back in the late 90s, and then he combined it with our ALE formulation around 2014. And this calculation was done by the team in Zurich. And they've since done, actually, they've lit the flame on this and have done the combustion with the expansion stroke. But what's interesting about this is that what compressed turbulence looks like is that it's more turbulent at top dead center than it is at bottom dead center, because the density goes up and so the Reynolds number goes up. And I mean, who would have guessed? I wouldn't have guessed. Let's see again. Okay. Here's another calculation. This one is somewhat similar to something I did back on Blue Gene P in 2009. I did a 217 pin calculation that's been splashed all over the place. This is a 61 pin calculation, but it's with a blockage, which is kind of cool. This was done by Iliam Rizari, formerly at Argonne, now at Penn State. And I have some statistics for this. This was done with NekRS on Summit. It's 4.5 million elements. We are routinely on Summit crushing records that we used to set on Mira. I mean, Mira, you know, a Mira hero calculation is pretty ho-hum on Summit. So again, this kind of gets to the user's perspective of exascale. We're still only at pre-exascale, right? Go beyond that, this is going to be like what you do before breakfast, which is what we want. So this is 1.5 billion grid points. It's using, you know, ho-hum 480 V100s. That's 1/7 roughly of Summit. This is N over P of 3.2 million. So that's what that tells us, and what it should tell you by the end of this seminar is that we could actually effectively use more processors, probably another factor of 1.5. And so we could get that 0.586 seconds per time step down to about 2/3 of that. So somewhere around 0.4 seconds per time step. A few more statistics on this. This was a 36,000 step run in 6 hours. So effectively, the whole calculation was 60 hours on 10% of Summit. The pressure solved constituted 85% of the runtime. That was using P multigrid with Chebyshev-Schwarz smoothing, and with Boomer AMG for the coarse grid, which took about 34% of the runtime. And the advection for this was second order characteristics. So the CFL was 1.5. So that'd be a 3 times larger time step size than if we didn't do the characteristics method. But you don't get a 3x reduction in time to solution because the pressure solves go up, and also, well, in this case, only a 10% overhead for the extra advection work. This is one of the few calculations where we actually have a head-to-head comparison between Mira and Summit. This was done by Ramesh Balakrishnan at ANL. In the last couple weeks of Mira's life, he got access to the whole machine. Now, the stats I have are not for the whole machine run. But so this is 500,000 ranks, so 262,000 cores. Mira had 800,000 cores. The best way to use it was C32 mode, so you'd run 2 ranks per core, and you get like a 1.5 speed up by using that extra rank, but you might as well do it because you're occupying the core anyway. The N over P was about 2,000, which is kind of standard for Mira. About a ½ second per time step. That's also pretty standard for Mira running at the strong scale limit. NekRS, we're running 528 V100s. N over P is 2 million. Again, that's our strong scale limit. And 0.14 seconds, 0.145 seconds per time step, which again, this 3-to-1 ratio is typical of what we're seeing as a comparison between Mira and Summit as our users would use them. How would our users use them? They're running for days. They'd rather run in 3 days than in 30 days. So they are always running at the strong scale limit. So we'll have a lot of discussion about that. That 3.4x speed up was not anticipated. If you look at our 2020 BP paper, you'd see that was not a foregone conclusion. Some of the speed up has come through algorithmic developments and things that I'll talk about as I go forward. Okay, so again, it's a little difficult. Okay, so the objective is to develop fast, efficient, scalable code for simulating turbulence in complex domains on exascale platforms. Our approach is high-order spectral element discretization. So the idea is to reduce the number of grid points per fixed Reynolds number or increase Reynolds number for fixed n. Also to ensure everywhere that the cost scale is O of n. We're looking at n is let's see what the largest we've done, I think, is 175. Well, I'll go with 60 billion so far is the largest we've done, 60 billion. Okay, we have fast GPU kernels on each node, due largely to tremendous work by Tim Warburton and his group as part of the CEED project. So again, we've benefited hugely from that. And then strong scale as far as possible, because that's how our users use these machines. And we designed to minimize communication and the coarse grid solve overhead. Okay, so I think most of these I've covered. I'll go to the second set of bullets. So, we want to be able to support a broad range of physics, a large number of boundary conditions. So many years ago, I ported NEC to what was a cutting edge supercomputer. I won't say, because that will say how many years ago it was. Well, it was in the 90s. There were 74 boundary conditions. The way I knew that is because that machine didn't support character strings. So I had to assign a number to each one. It was very painful. After 10, I quit. But I realized, okay, that's the difference between an academic code and an industrial code. How many boundary conditions? You can just ask people, how many boundary conditions do you support? And if they say 3, you say, okay. So it is kind of a measure of utility. So turbulence models, we are continuing to learn. We actually have a very nice collaboration with the ExaWin team, and that's absolutely been wonderful because we've been comparing a lot about turbulence models, and they have educated us, and our turbulence models have improved as a result of that collaboration. We support compressible flow, low Mach combustion. We support ALE. We do not yet support non-conforming meshes, but by the end of the summer we will. And that's, I'll leave it at that. We do support it in NEC 5000, but not in NekRS. We also support state-of-the-art Lagrangian particle tracking with one-way, two-way, and four-way coupling. Again, that's right now only in NEC 5000, but it will be, at least some of that will be in NekRS by the end of the summer. And we support Maxwell, Poisson, Nernst, Planck. Right now, all that's only in NEC 5000. Okay, so what about strong scaling? So I want to just have a little discussion about strong scaling and where this strong scale limit idea comes from. This is a classic type of plot you might see in a paper. And people do, okay, here's my strong scaling result. And, it goes down nice and linearly for a while, and then it departs. And now, first point of discussion is, would a user stop here, yes or no? Or would they stop here, or would they stop way out here? It's really a choice of, I don't know, it's a personal choice. In CEED, we've just picked 80% as a reasonable number, but the user obviously can pick whatever they want, depends on how big a hurry they're in. And what we notice is that this red curve strong scales better. I can get out to more processors than I can with the blue curve. So what's up with that? Well, the red problem is 4 times larger than the blue problem. And if instead I plot these as number of points per rank, we see that the curves are virtually identical here. This is for B. This is just for the Poisson solve, I guess. It's not actually for a Navier-Stokes solve, but the Navier-Stokes looks similar. It's not that different. So the really important thing here is for a given machine is number of points per rank. That the magic changes as you change machines, and there are other ways to plot the data, but this is certainly one of the more interesting parameters. Okay, so what are the observations? Time to solution goes down as you increase P, especially when eta is 1, meaning you're on this dashed line here. Okay, as long as you're on this dashed line, this job's running so 1, and then 2, 4, 8, 16 times faster than this one. The total number of joules consumed is identical. I can occupy a machine, for 10 hours with 4 cores, or 1 hour, 40 hours with 1 core. I burn the same number of joules, but in one case I get my answer back faster than if I use fewer processors. And all the users are very smart about figuring that out. They do it. They run. Next day they go, oh, I'll double it. And it ran twice as fast. I'll double it the next day, and so on and so forth, until they find this point. And then they'll kind of figure out where to land. All right. So a big question for me in my research is, okay, I'm a developer. Could I push this knee in the curve? Could I push it down? Right? My users would be really happy if we could do that. So rather than just say, well, here it is, what it is, we should say, what's going on? Why? Right? That's what we want to understand. Okay, so here are the same 2 plots. Now we can do a little more rescaling. We can, with an appropriate scaling of this line, we can get it down to a constant, right, which is the parallel efficiency. There's actually a little bit of the traditional cache bump here. And then the parallel efficiency starts falling off. Or we can plot it as what Mark Taylor calls the grind rate. Some people call it the throughput, which is the number of DOFs times the number of iters divided by it's the amount of work produced divided by the amount of resources applied. And the amount of resources applied is the number of nodes times the time you occupy those nodes. And notice that curve is identical in shape to the parallel efficiency curve. So from here, you can just look. There's a couple ways to do this. If you want to take your peak throughput, then you look for 80% of that. That would be where you would operate. Or if you want to give yourself the gift of the cache bump, you could start back here and say, well, if I were saturating my workload, I'd get 80%, and I'd be out here. But that might change this points per rank. And you see it's about 2,000 here. This is on Mira. Okay. So here's what's interesting. The minimum time to solution, once I pick my 80% as my desired parallel efficiency, that number is fixed. It's basically how much work I have to do, which is a statement of the problem, times the n sub 0.8. So it's this value here, okay? So if this n sub 0.8 goes up, everything else being fixed, then my time to solve the problem goes up, right? All right. And then on the other hand, keep everything fixed and then speed up the machine. So if I double my rate of doing MDOFs, then my time goes down by a factor of 2. And so the unfortunate thing is, as we change, or not unfortunate, but it's just the complication is that as we change platforms, the MDOFs goes up. So certainly the MDOFs of a V100 far outstrip the MDOFs of a single core of Mira. But what's the impact on n sub 0.8? It's this ratio that determines, excuse me, the time to solution. So one way to think about that is somebody walks up and they say, hey, I've got this new machine. It's really cool. It's got these nodes. They're 10 times faster than what you have. You go, oh man, that's so cool. I'm going to be running 10 times faster. They go, oh, bad news. You need to put 100 times as many points on each one. And you go, oh, my time to solution just went up by a factor of 10. It's depressing, right? And that's kind of what it looked like 5 years ago. It was not clear which of these two was going to win the race. In part, the vendors really were not aware of this whole idea of n sub 0.8 because if you're designing for a fixed resource environment where you, okay, so I don't have that slide, I typically, or I often do. There's two ways we can think of high performance computing. One is you have fixed resource, meaning you've got 96 nodes in your lab and you're going to use them all. And you just want it to run as fast as possible no matter what. That's one, and so that's one version of HPC. The other version is you have this computing center. You're not using the whole machine, which means as far as you care or know, there's an infinite number of processors because I'm not hitting any kind of bound on how many processors I'm using. I'm stopping because I'm falling off this curve here, okay? And I want to minimize, subject to, let's say, 80% efficiency, I want to minimize my time to solution. And then the vendors and the developers have to pay close attention to this n sub 0.8 number, okay? Otherwise, the users are toast. Okay, so another way of, okay, this is not, that's okay. I just want to mention something about high order. And what we see is from this very extensive study done as part of the CEED project, remarkably, the time when you're running at, and the only time that matters in the scenario I laid out is T sub 0.8. That's where the users are going to run, okay? That time is almost independent of polynomial order, remarkably, okay? And that's all you have to say about it. And notice it doesn't say how big the problem is. It doesn't say anything. It's kind of a strange plot because it's independent of problem size. Because if you make the problem bigger, we'll use more processors. And we do that until you're using all million ranks on myriad, but most likely you're not going to get there. And the other incredibly cool thing about this collaborative paper is that everybody's a winner. FEM was the best on BP1. NEC did okay on BP3, and now this is the dashed lines are the vector forms of those equations, but we can just pay attention to scalar ones. DL2 did all right. DL2 did well over here, and NEC a little bit on the polynomial degree 8. So, but you know, these numbers are, and again, these numbers are for Mira. They may or may not change for Summit. In fact, I think the numbers are a bit higher for Summit. I don't have those graphs here, but if you look at the paper, they are a bit higher, which says that under this model, Mira is faster than Summit, right? So that's why I said earlier that it wasn't a foregone conclusion that in the Navier-Stokes Mira, they would win. Okay, so let me just jump into a little bit of math, so a little bit of spectral element stuff, and then a short section on parallel computing concerns. So we're solving the incompressible Navier-Stokes equations. The principal features of this are this nonlinear first-order advection term. The fact that it's nonlinear is not as important as the fact that it's advection, which means it just migrates structures, it migrates information, and the amount of dissipation is typically small because Reynolds number is large. And then on top of that, to make everything bad, we have this incompressibility constraint that has to be satisfied at all times. And that gives us the gating term, which is the pressure. And by gating, I mean it's representing infinitely fast acoustic waves. So it's intrinsically communication dominated. And it is the stiffest subset. So that's why we spend 85% of our time solving for the pressure. Okay. Okay, so what about the influence of scaling on discretization? So this is an old argument that goes back to Kreis and Oliger. In 72, they observed that if you're going to solve larger problems, you probably want to go to a higher order. And the argument goes like this. If I'm going to solve larger problems, and what is large? For us, large is if I have a turbulent length scale lambda and the domain size L is, say, is just 1, my final time is something like L over lambda, okay, if the speed is, well, let's do it the other way around. Let's keep lambda 1 and make L large. But my final time, I have to propagate stuff this far with speed 1, okay? So the dispersion errors accumulate linearly with time, all right? So you don't have the correct numerical speed unless you have a Fourier method. So there's always a difference between the correct speed and the numerical speed for each wave number. As the wave numbers get higher and higher, the error gets larger. And the error at the final time is proportional to this time. Okay, so it scales like this relatively large number times whatever your error is, your error per time step or your spatial error. Okay, so if I want my final error to be small, then I need this quantity to be much, much less than 1. Okay, and so that puts pressure on this numerical dispersion error. All right, and so therefore I really want to have my numerical speed be accurate, and I want to minimize dispersion errors. I've just shown here results at time of 3 of advecting a little Gaussian hill around with a resolution of 105 points with a 4th order compact finite difference scheme versus a 7th order spectral element method with a diagonal mass matrix. And you can see that at this resolution, you have these trailing dispersion waves, even for the spectral element method, but they are worse for the compact finite difference scheme, which has a good error constant, but it requires you to solve a system at every time step. I just use this as an illustration. I don't say it's the closing point of the argument. There's a lot to be said about this whole topic, but that's the idea. So the spectral element method is really just a high order finite element method. Padura noted that in his 1984 paper. However, it is qualitatively different, and it really struck me. Many years ago, I had the pleasure of having lunch with Bretzi and Madej. Bretzi's smoking on a cigarette. Okay. When are these finite element guys going to get it? You've been doing P equal 32 for 20 years. I said, okay, it is qualitatively different. I mean, it's just a p-type finite element method, but it's not, right? It's the fact I can take n equal to 100 in NEC, no problem. Been able to do that for 25 years. It's the fact that we have this matrix-free form, which is really central to the speed of the method. So, of course, we have exponential convergence with n. Remarkably, the thing that has survived as good about this method is not so much the exponentially fast convergence, because people are able to do accurate turbulence simulations even with relatively low order methods, but it's the fact that it's fast. It's kind of surprising. But here's our exponential convergence. Of course, no user would want this. Nobody says, I need 10 to the minus 12. If they did, this is a great code for them. They'll say, I'm really happy with polynomial degree 4 and 10 to the minus 2. So but again, it is this exponent, you double the number of points, the error goes down by 4 orders of magnitude. So it's quite different than second order convergence. Another argument for these methods was noted in Gottlieb and Orszag, which was even for solutions which are pointy and for which it's provable that these things do not have exponential convergence, it's probably only going to be third order convergence, they do remarkably well. So here's, these are all 32 by 32 grids. This is 8th order. It's just an advected cone one time around. And the reason is that there's a lot of low wave number content in this solution, which is advected correctly by the high order method, even though the convergence is only algebraic. Okay, so we have a lot of small scale structures in turbulent fields. Here's one of my favorites. These horseshoe vortices evolve into hairpin vortices as they break up, and you can kind of see the structures here. You have to look closely. But this flow is turbulent, but it's definitely not random. You have to be pretty accurate to get that kind of transport. Okay, so costs are dominated by the iterative solver costs, which are proportional to iteration count. So we spend a lot of work on that. And then the matrix vector plus the preconditioner cost, and really the preconditioner cost is quite dominant. And we'll see some slides on that. So here's the real cost advantage is coming from the fact that we have locally lexicographically ordered data. So if I want to differentiate this, with this tensor product form. So the derivative in the R direction, for instance, ends up being a matrix-matrix product or a tensor contraction in higher space dimensions. So it's fast. So we have 2n squared reads, 2n cubed ops. In 3D, we have n cubed reads and 2n fourth ops. And so the design performance objective is everything should have only O of n, en cubed storage, meaning O of n storage for E elements, and O of E n to the fourth ops. So we don't want n to the fifth or n to the sixth. So the other thing that's kind of interesting about this, which is you could argue is part of the reason it took a while to take off, is that in 1D it's pretty much a loser because you have a 1D vector of length n, but you have this operator that's n squared. Okay. In 2D, okay, now I'm doubling my amount of data that I'm pulling in because my operator is n squared and my data is n squared. And then finally in 3D, well, now your operator is subdominant, right? That the dominant work or the dominant operation here is to fetch these n cubed values from memory. Okay, and everybody has to do that, whether you have a high order or a low order operator. So as you change the spatial dimension, it's kind of a load leveler, and it changes how one goes about designing these things. Our nodal points are based on the Gauss-Lobato-Legendre points. So there's two motivations for that. One is stability. If you use uniform points, it's going to be absolutely terrible. The condition number will be exponential in n, whereas it's for the stiffness matrix, it's O of n cubed with the Gauss-Lobato points. And plus you get accurate quadrature, so we can get away with a diagonal mass matrix. Again, I'll talk about that in a few slides. And so here's the matrix-free form for the stiffness matrix in deformed geometries. We have to basically compute a bunch of gradients in the canonical reference frame, and then we collocate with pre-computed Jacobian diagonal mass matrix, and then the metric terms coming from the geometric transformation. Okay, so there are 6 loads here. These are all diagonal matrices. It's a symmetric tensor. So there are 6 n cubed memory references per element, plus n cubed to bring in the data. So the total number of memory references is 7 times the number of grid points, essentially the same as a 7-point finite difference stencil with variable coefficients. However, we can go up to whatever order of accuracy you want. Our data exchange, another kind of interesting point here, the amount of data that's exchanged is just the stencil is of depth 1. You only have to exchange surface data. You don't have if you had a 7th order finite difference stencil, you'd have a fairly deep stencil to exchange here. So that does not happen in this case. Okay. Leading order cost scales is the number of grid points. A kind of cheesy way to look at this is suppose you're doing Jacobi preconditioned conjugate gradients. There's only one operator in this entire step that depends on the order of the operator. That's this one. And we've already shown that we can make that fast. So it's not surprising when you find 2 codes that are fairly mature where they're running at pretty much the same time. And we've seen that for a study done by Edmund a while back showed that NEC 5000 and OpenFOAM have exactly the same execution time over a factor of 16 increase in the number of processors. Okay. So this is just one point that shows, and we've seen that before in a prior slide, that the CPU time is essentially independent of n. And here we see it. This is for BP5, so it involves some communication again, which is a load leveler. This is from our BP paper, and this was Tim Warburton's study. So it's remarkable. All right. Stability, that was a big issue for us for a very long time. We could not do high Reynolds numbers. We found that a low-pass filter was like taking aspirin. It cured all problems. If you have any kind of high wave number instability, you take one of these, it will fix the problem. We dug in a bit deeper and found out that the real issue was because we were not de-aliasing the advection operator, and then you lose skew symmetry. So you can show that it's a linear phenomenon. You don't have to, it's not a nonlinear phenomenon. It's a linear advection issue. So that cured that, but we still use filtering occasionally. as an alternative, you could consider DG plus upwinding, and all the cool people do that, like the people I'm here with. Tim Warburton does it. Martin Krombeekler does it. All the cool people do it, and there's a good reason. It actually works. Do you guys, by the way, do you de-alias?
Yes.
Okay, so you're like me,
Yeah.
suspenders and a belt.
Yes.
Yeah. Tim Warburton's more on the edge. He doesn't de-alias, and I'd like to avoid de-aliasing too. But this, I think this is in the works for us in the future. All right. So here's the advection diffusion equation, which is our surrogate for Navier-Stokes with the different quadrature rules. So here's our N. This is our Gauss-Lobato-Legendre quadrature. Madej established, back in the 80s that this was stable and that's all you needed. And it's long been an argument of Orszag, which is do what you need for stability and nothing else. You don't have exact approximation. Why should you want to integrate to infinite precision? There's a paper by Madej and Ronquist where they look at the potential advantage of over-integrating when you have non-trivial geometry. And they make the recommendation that it doesn't really buy you anything, and if you want the extra accuracy, just increase N. Here, we do over-integrate, as I mentioned, in order to de-alias this, because the argument here is potentially a polynomial of degree 3n. And then here, there's also a debate, should I over-integrate, yes or no? I prefer a diagonal mass matrix, in which case I just do the n. But there's some potential accuracy advantage to bumping that up, for example, for the compact finite difference scheme. But I think that as you go to higher order, that advantage kind of evaporates. So those are the choices. There's a study by Mark Ainsworth. He looks at this question of how to integrate the du dt term. And the way to read this table from the paper is that if you use the full mass matrix with linear elements, you get the compact, what we all would recognize as the error term for the compact finite difference, or the linear finite elements with a tridiagonal mass matrix. So just think of it as h to the fourth over 180. That's the well-known constant. Look, first of all, the difference between that and the diagonal mass matrix, you go from h squared to h to the fourth. Okay, plus the constant goes by a factor of 30. So it's really quite dramatic when you have linear elements if you do use the full mass matrix. But as you get down here, it's less dramatic. Like here, fourth order. Don't interpolate this one as h to the eighth. I've never understood with Mark exactly how to interpret these. When he explained it to me the first time, I thought I knew what it was, but then later I studied it. I said that can't be right. But the constant, or the exponents are the same. Again, the constant's better here. But my argument is, hey, if you're not happy with this, just increase your polynomial order, and it will just drop precipitously, and you can retain the diagonal mass matrix. Okay. I won't go into this. This is just explaining how we do the Navier-Stokes, but the bottom line is we get a Poisson equation for the pressure. And so what are some properties of this? First of all, the conditioning does not improve as delta T goes to 0. Let's see if we have, that's in contrast to the Helmholtz, the viscous term, right? As delta T goes to 0, this becomes more and more diagonally dominant. But the pressure, why doesn't it get better? It's because it's infinitely fast, the acoustic wave, the physics. So no matter how small you take delta T, this thing's faster than that. So the conditioning does not improve as delta T goes to 0. It's almost all Neumann boundary conditions. It's just intrinsically the most expensive step. One thing is that you are solving nearby problems on each step. So you can use that to your advantage by projecting onto the space of prior solutions. And then the result is very often you only need a few iterations per step. We'll see some results for that later. But basically the idea is I have Bn, I have a way of computing some P bar of n, which is the best fit in the span of some, in this case, prior solutions, but they could come from anywhere, these vectors. You just take your space that you want to project onto. You insist that you have a conjugacy amongst the representative basis functions x sub I, and then the best representation of the pressure at time n is just the inner product of the xj's with bn multiplying each of these basis vectors, okay? That is the best approximation in the A norm to the unknown Pn, all right? So I subtract this off and I solve for this. Very often this residual can already be like 10 to the minus 7th. 1 or 2 iterations is enough. Here's a kind of cool thing. This delta P, because this is the projection, it's the best, is orthogonal already to this space. So all I have to do is take delta P and stuff it into this space. It's already A conjugate. I have to normalize it. Now, the problem is it's not quite orthogonal because you don't solve this to infinite precision. So you have to do one round of Gram-Schmidt, but classical Gram-Schmidt's good enough because it's already almost orthogonal. What makes these problems different from standard Poisson? Well, it's unstructured, high aspect ratio elements. These high aspect ratio cells are problematic. We have many different geometric configurations, so no single solver is the best. So we support a lot of solvers, and some of those we auto-tune through, so the user just ends up getting whatever is the best. And of course, we're interested in solving problems at the strong scale limit and pushing that as far as possible. So here's the funny thing about strong scale limit. If you just write down the complexity for multigrid, this came from a paper we have in 2015, you see N over P is everywhere, right? And so this time is independent of N and P. It depends only on the ratio N over P, except for one term, which is the coarse grid cost, which goes up with log P. And that's why this is such a bugaboo here. It's like, it's not going to, it's not, as P goes to infinity, it's real. So if you don't see something on 400 ranks of summit, you might see something on 4,000 ranks of summit. Okay, so consequences of strong scaling, another kind of curious thing I had to fight with people at Argonne about. So, you know, suppose this is my complexity model. Work divided by P, that's the N over P type part, plus this communication overhead. And suppose it's 80 and 20 seconds. And suppose you come along and you improve it. You can get it down to 5 seconds. A lot of people say, come on, be focused on the 80, not the 20. You're going to get 15% gain. What's the point? No, the point is that all of our savvy users will immediately increase the number of processors by a factor of 4, and they'll run 4 times faster. This is why this is so absolutely critical. And same energy, same node hour consumption, right? But instead of 4 days, they rate 1 day. So it's a subtle point, not highly appreciated. Okay, so what have we found? KSPs are absolutely mandatory for our solvers. We typically use CG. We sometimes use flex CG, but it's not a KSP. So primarily we tend to use GMRes, and we can afford to do so because the number of iterations is typically going to be small per step. You know, we're looking at problems, or we might even get up to 10 to the 12th in the near future. So preconditioners, we have overlapping Schwartz, P multigrid with a variety of smoothers, and then FEM-SEM, which is this equivalence between a low order finite element operator and the spectral element operator, which requires a scalable AMG. So some of our PMG smoothers, Jacobi, that by itself is not so great, and that was discovered in, or discussed in early papers by Ronquist, Madej, Munoz, and Padura. Line smoothers introduced by Heinrichs, and also by Ji Shin somewhat later. Block smoothers, those are using fast diagonalization. Multi-level weighted additive Schwartz, low cost but high iteration counts. It's better than the block smoothers. And more recently, Chebyshev-Jacobi. So Tim's group adopted this, also Martin Krombeker's group, based on a paper. Well, I think kind of the first paper in this space is Adams and Tumanaro and co-authors. And so then in the last year, Malachi Phillips at Illinois has extended the Chebyshev-Jacobi to just combine Schwartz with Chebyshev, and so we have this Chebyshev-Schwartz methods. Okay. Here's a little note about SEM-FEM. The basic idea is that there's a spectral equivalence between a finite element mesh or a finite element operator on the Gauss-Lobato points and the original operator. That's clear to see the lower bound, and the upper bound is a little maybe less self-evident. But there's a nice explanation of this in Orsag's 1980 paper on general spectral methods. One thing that's a little bit tricky when you do this in 3D is how to tessellate the hexes. And it turns out it's kind of important to not have a 27-point stencil, because the underlying spectral element stencil is star-shaped unless you have geometric deformation. So something that gives a star-shaped stencil is somewhat better. And that's what we developed with Pedro a few years back. Here are the number of iterations compared to our hybrid Schwartz. So this is not with Chebyshev, this is just our classic additive Schwartz. Clearly a lot better, and it's sufficiently better that it wins even in time per step. So we're down to about 1 second per step. I do not recall which platform this is on. Okay, so some recent Schwartz developments. Here's additive Schwartz. Here's Chebyshev Jacobi. So that outperforms our additive Schwartz, no question about it. Well, in terms of iteration count, in terms of time, not quite. They're kind of more or less on par. But the idea, so the idea of the Schwartz is that for each domain, you extend the domain out by 1 grid point. You solve the local problem using fast diagonalization, so separability of the operator. Even if the operator is not separable, in the case where the geometry is deformed, we just pretend that it's a box of the right dimensions, and we write down the separated operator. This can be extended to more general operators in a fancier way. A really nice paper by Will Pasner and Olaf Persson, and some work done by Pablo Brubeck subsequently, and several other authors actually have looked at that too. But we just do the dumb thing, which is just write this down. And so 2 contractions, 1 diagonal divide, 2 contractions. So in 3D, it's 3 contractions, a diagonal divide, and 3 contractions. So it's very fast. It's actually faster than the forward operator. And you can see with the Chebyshev acceleration, this does improve upon the prior methods. Okay, so Malachi did an extensive study for SIAM parallel processing. I just want to point out that this one, for this particular geometry, SEMFEM crushes the competition. So the x-axis is time per solve. You want to be to the left and up. The throughput is higher. And this is one example where SEMFEM totally crushes. On the other hand, for P146 here, SEMFEM does not crush. But for P1568, well, it barely wins. But it's hard to predict which of these is going to be a winner. All right. High aspect ratio elements are a bugaboo. If you read any of these papers, they say, paragraph 1, assume shape regular elements. Now proof. Okay. And, you know, a lot of times our users walk in and here's their mesh. And it's like, well, okay, this isn't exactly shape regular. This is why the Schwartz method, which should have order independent convergence, it does not. Initially it does. They track each other, and then this thing stalls out. What is this thing doing for the last 140 iterations? It's computing this mode, which is not captured by either the coarse grid nor by the local Schwartz solve. So these high aspect ratio cells are all this solution that you see here is just the difference between the solution at this iteration and the one at this iteration. So most of your time is spent computing this. It has nothing to do with the physics, which is all down here. You can help yourself. You can apply a little mesh smoothing. This iteration comes down by a factor of 2. This is work done by Caton as part of his PhD dissertation, and he looked at lots of examples and was able to get significant speed ups. Okay, so extreme scalability. Here's a case: 51 billion grid points, 100 million spectral elements, 352,000 pebbles. We're running on all of Summit. Pre-tuning, we're at about 0.6 seconds per time step. So this is the straw man. This was using the default settings in NekRS at the time. These times I think are for 2,000 steps. Yeah, so that's why it's a half second per time step. So notice the coarse grid solve is 45% of the time, preconditioner 78% of the time, pressure solves 90% of the time. So here I am, I'm just a user. I'm in a quandary because I can't go and rewrite the coarse grid solve. What can we do? Well, what we could do is put more pressure on the higher levels of the P multigrid to try to reduce the number of iterations, thereby reduce the number of visits to the coarse grid. And that's essentially what we did. We'll see those results in a minute. But the this problem is communication intensive. It's an all-to-all communication. There's too little work to keep the GPU happy. Kernel launch overhead is large, and there's system noise. So here's an example of system noise on Summit. This is what it should look like, and this is what it looks like here. In this region here, we have a 10% performance drop. The green and blue are communication intensive things. The red is not communication intensive. So it is not a daemon running on the node. It is a network issue, which is causing this boost up. So that hurts us at the strong scale limit. Here's something else you can do. This is from our CEED MS37 report. I think this is one of the biggest breakthroughs in the CEED project. And I was so excited when John Sylvain shared this. Here's one of these curves of throughput versus degrees of freedom per processor. As the problem size gets smaller, the throughput goes down, and so you have this n sub 8, sitting here at maybe at 1 million, depending on how you read it. He was able to get this way down by a factor of 10, down to 100,000. So you can push this strong scale limit out, and he did that by writing very large GPU kernels. It was a hero's effort, but it was extraordinarily well worthwhile. Because now there's only one thing left, that's the MPI overhead. You can do things to improve communication. In NEC, the gather scatter, which has done all of our stencil calculations or matrix vector products, sparse distributed matrix vector products, go through gather the GSLib. It chooses one of 3 algorithms: red, pairwise, green, crystal router, which is a generalized all-to-all, or blue all-reduce. And for every topology, this is the number of points in the given topology, it does a test and it picks whichever of these is the fastest. So red, this is the fastest, is faster than the generalized all-to-all. Over here, generalized all-to-all wins. This is on a log scale, so these are significant wins. And then down here, the all-reduce wins. Now this is on blue jeans, so the all-reduce is ridiculously fast, about 4 times the latency. If you run the coarse grid solve, this is James's AMG, with pairwise only, it's about 6.5 times, a little bit more than that, faster than if you run it with the tuned communication. I have more to say about that offline if somebody wants to talk about that. Okay, so back to our problem. Let me go ahead. We did a lot of tuning. We were able to get that 0.68 seconds per time step down to 0.24. Part of it came through projection, by adding projection, which was not really in there beforehand. And so I'll just show that plot here. Here's the times. If you don't project onto the right-hand side, here are the times. These are Navier-Stokes times if you do project on the right-hand side, using 30 vectors. All right. So this was a win. We can now do, in 6 hours, we could do a single flow-through time on all of Summit. Again, all of Summit is a fraction of the exascale machines. Okay. I guess I won't dwell on this too much. There are, just to point out, hero work by Tim. NEC will pick the fast. We have several kernels for all of our work-intensive kernels. And NekRS runs the timing and picks the fastest one for each configuration. But for the fast diagonalization method, we're seeing for P equal 10, 8 teraflops FP32 on the A100 and 5 on Crusher. So it's running fast. Okay, so a few Crusher results, and then I'm done. So Crusher is in black here, Perlmutter is in blue, and Theta GPU is also in blue, and then Summit is in red. here with Summit, we see 2 million, the 80% parallel efficiencies at about 2 million points per rank, with Perlmutter at about 2.5, and with Crusher at about 3. Now, this is a kind of a curious story, and it makes me question my original principle, which is, you're going to run at 80% efficiency, and I'll explain why in a second. Let's look at this plot. This is the Jed Brown plot, time per step on the x-axis, and the y-axis is throughput. This curve, you want to be up and to the left. Crusher is everywhere above Summit on this plot. So total win, right? But if you adhere to our original mantra, which is I'm going to run at the 80% mark, you're kind of burning yourself. So I would have to look deep inside to decide where I would run on this machine. But this dash curve is if you run Crusher with a non-multiple 8, any number of ranks that's not a multiple of 8. So just beware. That caught us by surprise. Okay. And then the T-flops, on theta GPU at the highest, at the peak, not at 1/2 strong scale, but we're seeing 0.91 T-flops for the Navier-Stokes solver per GPU. On Crusher, about 0.64 T-flops and 0.48 on Summit. So overall, we're quite happy with how things are running. Okay, so so this was the question I wanted to, this is kind of what I started thinking about weeks ago. This was a real question I had. This is a hero calculation from a few years ago done by the KTH group, Philip Schlotter's group. If I wanted to redo this on, say, Perlmutter, for example, how much time do I have to ask for? How many A100s? How many A100 hours do I need? How many node hours? Okay. Well, it's got 3.2 billion grid points, 35 million CPU hours were needed. Okay. So with 3.2 billion on Perlmutter, I need 3 million, actually 2.5 is on what we saw before, but let's just go with 3 million. So I can use 1,000 A100s effectively, right? I probably would not use a lot more than that. I would not use 10,000, I'd use 1,000. Each of these is about 300 times the performance of a CPU. I base that on several things I won't explain, but, well, I have this cheesy V100 knockoff that's 150 times faster than my Mac core, and A100 is 1.5 times faster than the V100, and the V100 is faster than that. So I'm figuring it's about 300 times a single CPU. So I'm going to need about 110K GPU hours, so about 110 wall clock hours. It's not terrible. And then the number of nodes, well, I don't know how many nodes on Perl. I think it's 4 GPUs per node.
Yes.
Yeah, so it'd be 250 times that number for the number of hours. Yeah. Okay, and that is it. All right, so I've tried to give an overview of scaling issues for Navier-Stokes, where people are most likely to run, give or take, several preconditioners, importance of the coarse grid solve, and then, these new machines are really delivering about 3x at the strong scale limit. Some of that is coming through new preconditioners and highly tuned ALCA kernels, overlap communication computation, bless you, and mixed precision preconditioners, and then on-the-fly tuning everywhere. I mean, we tune everything on the fly, and it's the only way to go. You don't want your user in the loop, right? Did you try that? Oh, I'll go back, sit in the queue for a day. You can't afford it. So, all right, thanks everybody, and I apologize. Oh, I wasn't too bad.
No, that's great. All right, thank you, Paul. We can actually clap here for a stand. Hey, that's great. All right, we had about 40 people online in addition to the 4 West. So excellent talk, very interesting stuff. A lot of the things that we're also interested in. And you showed some of John's results. That was great. Any questions for Paul? In person or online? Please speak up.
You talked a lot about this 80% efficiency level.
Right.
And you're sort of stating that for this whole big code you're running.
No, think of it this way. I'm stating it for any user of these HPC machines. Take your favorite machine. Let's say Summit, because I know how many nodes there are. There are 27,000 GPU nodes. I walk up to you, how many are you using? 300. Why 300? Why not 600? And at some point you'll answer, oh, because I don't get any more speed up.
Yeah.
That's the point. It doesn't matter what code, what simulation, what physics. Why are you using 300 and not 600? That's the question you should ask. Right? Okay.
And from a developer's perspective, though, if I've got a code that I'm trying to improve the performance of, and I assume my user is going to be wanting to run at this 80% efficiency
Right.
level, you have different components of your code, and presumably, my assumption is that those different components might have different
Scaling.
different scaling,
Right.
different places where they hit this 80%
Right.
efficiency
Right.
level.
Okay, so that's a really good point. This is one of the coolest things. This was a statement by Jed Brown at last year's AM. Of course, the annual meeting. The coarse grid solve does not have to be efficient. It just has to be fast. Right? You don't try to get everything at 80%. You get the ones that are slow to be fast because they're holding up everything else. Right? So I don't know if that answers your question. It's an interesting way to think about it. It's like, no, this thing is the bottleneck. Everybody's waiting on that. And I don't care whether that's efficient or not. You might care at some point if you can't take that argument too far, because if it's 100% of the time, then it has to be efficient somehow. But yeah, but it's a curious thing that really for the coarse grid solve, all you need is, can I make it fast?
Right. So yeah, like in the example you showed, the course grade was like 30% of the time or something.
Right.
Like that.
It was 45% for the big one, and then we got it down to 11 by.
And so you're really worried about scaling for the rest of it, and then you're just sort of stuck with this coarse grid solve that's just a chunk of time. And you're not really worried so much about how it's scaling. You just want it in absolute time to go as fast as
Right. Exactly.
Okay.
Yeah. Yeah.
In some sense, when Paul says coarse grid solve, keep in mind, he has already polynomial reduction. His coarse grid solve is the first order
Yes, yeah.
problem, which is pretty big.
Which is actually because we're about ready to do 1 billion elements. So now our coarse grid solve is going to be 1 billion.
That's where
So-
AMD
Yeah, I know
takes over.
coarse grid.
Yeah. So coarse grid has
Different-
changed its meaning. It used to be, say, we ran one spectral element per processor. So the number of degrees of freedom is basically proportional to the number of elements. So we had 1 or 2 unknowns and per rank, but we're running at 1 million ranks on myriad, right?
Yeah.
Now it's different. We're running 8,000 elements per processor, and so I have 8,000 degrees of freedom per rank. So technically, we could coarse them down further. So if we're running on all of Summit 27,000 ranks, we'd have only 27,000 degrees of freedom. Now, I think if we do that successfully, if we can make that transition happen in a very efficient way, I'm sure we have hands down the world's fastest coarse grid solver for that problem. It's a direct solver. It's 2 matrix vector products, bang, boom, boom, log peak communication time. I'll put that up against any coarse grid solver at that scale, but it has a work complexity that goes like n to the 5/3, where n is the number of course would be 27,000 in this case. So that doesn't work when n is 1 billion, and work complexity of n to the 5/3 totally bites you. But if n is 27,000,
There's a bit of an analogy also with the coarse levels in multigrid. You know that they're not efficient. They're not using the
right? Yeah,
but
exactly.
they only have to be. They just need to be fast because you're visiting them a lot.
Yeah. Or yeah.
I'm wondering if that kind of mindset still applied here, because the coarse grid is sort of this larger. Your course grid is sort of what I think is a fine grid.
Where you start, yes, I know.
I'm working on AMG, so.
Right.
So okay, I have a question. It's about the mass matrix and the diagonal portion. I know that in for the type of problems that Navier talks, you don't have jumps in coefficients or anything like that, but you can still have elements with highly deformed geometry.
Yeah.
And then non-trivial Jacobian. Is there any if the elements are highly deformed, is in your experience diagonal mass matrix still okay, or should you integrate more?
You're talking about for the du dt term?
Yes.
So here's how here's where I might cave on that question,
Mhm.
or, you know, I'm attracted.
Cave means not that.
Right, cave means not that.
Exactly, okay.
I might cave in the context of Navier-Stokes,
Mhm.
because if I go forward with the argument which says, well, just bump up n, well, then your pressure solve goes, I mean, everything goes up, right? And you, so what you could do is the Helmholtz solve, you're already solving, you're already doing
Mhm.
a CG solve, right? So having a you don't need a diagonal mass matrix there. You still have to invert the operator because you have the Poisson part. So maybe just go ahead and add, you know, and use that full mass matrix in that step, because that's where that DU/D2 term shows up. And I haven't done that yet because it was harder than I mean, it wasn't something I could do in an afternoon,
Okay.
because I had to kind of go through the whole code to find every place that that's referenced. And I did make an attempt at it, but it didn't work, and then other things got in the way. So that might, you know, we're already doing a solve, so why not incorporate the full mass matrix?
Okay.
And especially in the complex geometry, I like that idea. I haven't really thought about it in that context.
I think we tend to have more deformed elements maybe than some of your applications.
Right, so maybe it matters.
Maybe it matters for us more.
Yeah.
Okay.
Yeah.
Okay, other questions? We still have about 20 people online. Do you wanna, can you bring up the slides that you had from
Yeah.
the comparison of the different machines? I just wanna poke you at this. Well, first of all, I will say you've had probably the most impressive and beautiful simulation results in this whole seminar series so far. Not this one.
Next one.
Let me see. This one, for example.
Yeah.
Yeah. So, I mean, you were commenting on Crusher,
Right, it uniformly outperforms Summit.
Crusher versus Summit, but what about the, you know, A100 machines? Do you want to comment on those?
Perlmutter,
Yeah, for example.
well, this is a stunning result. I mean, seeing here.
So they seem,
0.015, that's like a factor of 10. You know, we're kind of used to production runs at 0.15.
yes.
Now, you're way down in parallel efficiency here. So you're really burning up your CPU hours. You're down here at, you know, 3.5, you're, right?
But they
you-
uniformly seem to be doing really, I think you can say that that's a good product there.
It's a good product. Well, again, though, if you come back to, so let's ask ourselves where we would run. So we can go down here. Misun did an extraordinarily extensive study.
Yeah, let's look at the map.
Okay, here's Perlmutter. So Perlmutter is, oh yeah, I put it here, 2.9 million. All right. Oh, here, we can just see. All we have to do is ask ourselves above the red line, what's the amount of time per step? So here it's 0.038 for Perlmutter at the 80% mark.
Mhm.
Here's Crusher, 0.0748. So about a factor or two slower.
Yeah.
And then let's look at Theta GPU is a loser. Let's see. You know, well, it's not that bad. And then Summit is 0.04. See, Summit at the strong scale limit is technically faster than Crusher.
Yeah, but you know, Summit and Perlmutter are the same family. They're both.
Oh, I see.
NVIDIA machines.
Yeah,
you
they're
can see
NVIDIA.
the improvements there.
Well, they've been so here's the question that I ask myself, not just as like a developer, which I'm unfortunately not these days, but from an architectural standpoint, okay. And of course, this is exactly where Tim has had a big role, right? Tim and Noel.
Yes.
They're telling the AMD guys why this is important, what they could do to improve the N sub 0.8, because that's, you know, without making the hardware faster. See, that was my big worry going into this is like, two things. First of all, most of the vendors were totally unaware. They just looked back at you with this. I had a guy from NVIDIA say to me years ago, "You're not solving big enough problems." No, you don't understand. You want to have a small problem on each processor.
And processors, yes.
Yeah, and moreover, DOE was kind of hiding it, right?
Yeah.
Because they were worried about being embarrassed that the machines would not be faster than the machines they already had on the floor. And what bothered me about that is, if you're not telling the vendors that they got to fix it, guess what? They aren't going to fix it. If you don't put the bar out there.
So if you go back, I mean, to the table with the tables, and obviously already the NSAP 0.8 on Crusher is, I don't know, whatever it is, a quarter larger than the one on Perlmutter. So
4, yeah, and here it's 3 roughly. I mean 2.8. Here it's 4. Well, actually, this red line I think should be shifted down a bit.
Theta GPU
There we
looks
go.
a little off.
This one's better, 3.36.
I don't know.
Theta GPU is totally a loser machine. We don't know why.
Something's off there.
Yeah, I mean, you can see if you're not running in parallel, but something's off with the network, or we don't know what. And we've brought this to their attention, and they're somehow looking at it. But
Okay.
yeah, we don't know about Polaris yet.
You don't have Polaris results?
I think that we have a few, but nothing comprehensive like this.
That should be up there with Perlmutter. All right. Last chance. Questions from anyone?
Oh, I want to say a couple more things about these plots.
Go.
So first off, this lower left panel is totally work intensive. It's just the right-hand side, and it's de-alias. It's the de-aliased operator. It's totally work intensive. And you can see here, Crusher is almost as fast as Perlmutter. Okay. On the other hand, here's the coarse grid solve.
Yeah.
So this tells us where to look on Crusher. It's in the communication, right? I love looking at these plots and then reversing what must be going on the machine.
Well, that's the point. Inside, right? Right?
Yes.
That's what they should be used for.
Yeah. And over here, you can also see, look at this, the way this blue curve is jagged. Okay, that's the coarse grid solve. You can see its direct impact on solution time here on Perlmutter.
Mm-hmm.
Okay, so that, of course, you wouldn't run out here. So in fact, you might stop paying attention after some vertical line here.
Mm-hmm.
So it's not really fair if this is out in the region of non-interest in some sense. So again, that helps. Understanding this n sub 0.8 helps in guiding what you should focus on in plots like this. Don't be focusing on regions where people aren't going to live.
So, I mean, vendors are looking like proxy apps.
Yeah,
Are we just not giving them the right
partly.
incentive there to look at the right thing?
Yeah, it was really hard to write a proxy app for a GPU-based machine based on our experience with Myriad. Scott Parker and I were like, how big a problem should it be? You don't know. We were like 2 elements per rank. It's not clearly the wrong thing to be saying for a GPU. And then Jed said to me, n sub a half. I go, oh, thank you. That's all you have to do. Pay attention to the n sub a half. And now we use n sub 0.8, but all you need is that number. So, yeah, it's hard to write for like some weird future architecture that you don't understand.
I think certainly
Hard.
we didn't anticipate I mean, as you said yourself with our first paper, we didn't anticipate some of the characteristics of this GPU machine. Some of them we did,
Right.
but some of them we didn't. And the overall how things ultimately ended up being, I don't think we could have predicted it.
Well, I was
guessing,
really,
but I think things were,
Yeah.
things were moving.
Yeah.
And it's co-design. That's why you have to be involved the whole time.
I mean, this is just mental.